Then we're going to look at addition and subtraction formulas. So we're going to come up with a bunch of formulas today. I guess I should say, etc. We're going to do a little more than just the addition and subtraction formulas. A lot of these are really useful and important. They're going to come up again in calculus. It would be possible, but kind of difficult to just memorize them all, and probably not useful. It would be useful to know them all, but there's some patterns that you're going to have to look for yourself. I'll point out the obvious. It's not necessary to remember 12 or 14 formulas that we're going to do here today. Some of them you can just see right away how they fit in. But again, these are important. You'll see them on the homework. You'll learn how to use them a little. It's not really important that you know where they come from. It's not required, but I would feel delinquent if I just said, here's the formula, love it or leave it. What I find amazing is that they all pretty much evolve out of just one formula. In particular, we're going to look at what the cosine of x plus y is in terms of the other trig functions. And you may have seen this before. I don't want to be mysterious about it. The formula is cosine x cosine y minus sine x sine y. Seems like a nice result, if that's true, but why on earth? Why on earth could that be? So I'm going to show you why this is true, and then I'm going to develop all these other formulas from this one formula using what we know. You're not going to be required to reproduce this proof. All the steps are really straightforward, basic, but you might have to stretch your memory back to when you took geometry. This is kind of geometry and algebra and trigonometry all at once. So, here we go. We're going to start with a unit circle. We're going to label this point here A, coordinate 1, 0. And we're going to choose some arbitrary point in the first quadrant we're going to call P. And we're going to give a name to this arc. We're going to call it R1. Now, I hope some of you recall from geometry that if you have a central angle and an arc, that the measure of this arc is the same as the measure of the angle. In other words, we would call the entire circle, the arc length of the entire circle, we would call it 360 degrees or 2 pi. And this central angle has the same value. So that's step one. The next thing we're going to do is we're going to create a point Q, again an arbitrary point in the second quadrant. And what are we going to do with that? Well, so we have this is R1, and this arc here is going to be R2. So again, this angle here will be R2. I'm not sure if that's right. Let me make sure. No. Okay, so let me at least break this down. So arc AP, that's this, is R1, and arc QP is R2. Right. The last thing I'm going to do is I'm going to create a third arc down here in the fourth quadrant, but it's not going to be arbitrary. This is R2. So the angle here is also going to be R2. Whatever this R2 was, this angle here is R2. And we're going to call this point R. Capital R. So we have arc AR also equal to R2. Okay. This is a little, I mean, it seems a little arcane at this point. Why are we doing all these things? Well, basically, we're setting this up so that this segment here, AQ, is going to have the same length as this segment here, PR. Why is that true? Well, this is a chord, and the sector around this chord is R1 plus R2. You can see that R1, R2. This is also a chord, but as I set this up to be R2, R1 plus R2 is going to have the same length. Okay, that's our geometric setup for this proof. So what I need to do now is fill in the coordinates for these two line segments. We have A. All right, let's look at Q for a second. Well, the angle here is R1 plus R2. So from our trigonometry, we can see this is the cosine of R1 plus R2. And the sine of R1 plus R2. R1 plus R2, that's just an angle. Coordinates of P, well, since this angle is R1, cosine of R1, sine of R1. And finally, the point R here, well, this angle is R2, but from the unit circle point of view, this is negative R, right? So this is the cosine of negative R2 sine of negative R2. Okay, we have our three coordinates. We know that these lengths are equal. And now what we're going to do is we're going to use what? What tells us the distance between 2 points? It tells us the distance between 2 points.
Distance formula?
Distance formula. Thank you. Is somebody? Okay. So at this point, I'm gonna write this all out. I'm feeling very nostalgic. In college, I had an astronomy professor he was just a character. He was in his 70s, brilliant guy. He had this very, very subtle Georgian southern drawl. And he would come out every day and he would like fill up blackboards. He would just fill up. We had 3 blackboards, and then he would go and erase the first one and start writing again. He'd do that for an hour every day. We'd sit there writing all the deck, trying to understand what he was doing. I realized that could either like make you nervous or put you to sleep. I don't really want to do that, but it's just, there's a little bit of that here. Not too much, hopefully. All right, so let's look at AQ for a second. AQ is these coordinates and these coordinates. So let's apply that formula. So we get the cosine of R1 plus R2 minus 1 squared, that's the x-coordinate, plus sine of R1 plus R2 plus 0, plus 0 minus 0, squared. And that's AQ. And PQ, PR, I mean, that's going to be what? Well, okay, these are the coordinates here and here. So we have the cosine of R1 minus cosine of negative R1, negative R2. That's squared. And finally, minus the sine of R1 minus the sine of negative R2. That's squared. Okay, everything else from here is algebra. So we look at these two sides and we say, obviously, we want to square both sides, right? And then we want to expand this. So cosine squared r1 plus r2 minus 2 cosine r1 plus r2 plus 1. That's this piece here. Oh, this is nice. It's just sine squared r1 plus r2. Okay. So far, over here, again, I'm going to square this. Cosine squared r1 minus 2 cosine r1 cosine minus r2. I'll run out of room, but that's okay. Plus cosine squared minus r2. Okay, that's just this first part. And then we have to subtract what's in here. Sine squared r1 minus 2 sine r1 sine negative r2 plus, so being optimistic here, plus sine squared minus r2. Oh boy. Well, let's at least try and make our lives a little simpler here. What would be the cosine squared of r1 plus r2 plus the sine squared of r1 plus r2? That's an easy one. Yes? 1. All right, good. So let's just kind of cross these off. That's 1. Well, plus 1 is 2 minus 2 cosine r1 plus r2. All right, let's see if we have anything like that over here. You might want to note here, we have the cosine of minus r2. Why is it I can just eliminate that minus sign? Why can I say cosine of minus x is equal to cosine of x?
Because it's an even function?
It's an even function. Right. So let me go through. I have another one here. Here I have a sine of minus r2. Sine of minus r2 is not sine of r2. It's something else, right? It's an odd function. So what's sine of minus r2 in terms of sine of r2? Odd function. I hope you all remember sine of minus r2 is minus sine of r2. It's an odd function. So I can make this a plus, but then I have to change this to a plus also. And here, well, sine of minus r2 is minus sine of r2, but it's squared, so minus 1 squared is plus, so I can just do this. All right, let's see, do I have anything convenient here? Sine squared r, cosine squared r2 plus sine squared r2. That's going to be 1. Cosine squared r1, sine squared r1. That's just going to be 1. Is it? Oh, wait a minute. I think I jumped there. Everything here is minus, so let me distribute the minus first so we don't make any mistakes. Okay. Now this becomes, well, we'll just eliminate Okay, we're getting close. We're getting close, but I feel like something is not working for me. I feel like there's a mistake. So this originally was just a plus, right? So these are all minuses. And that's all right. Well, that's why I have notes. I can bail myself out. Oh, there's the mistake. This was always a plus, right? Distance formula. And these all become pluses. Okay. It could happen. All right, now I've got cosine squared R1, sine squared R1. That's 1. Cosine squared R2, sine squared R2. So those are 2, right? So I have 2 minus 2 cosine R1 cosine R2 plus 2 sine R1 sine R2. These are equal. Starting to look good. You can eliminate the 2 on each side, right? And then let's divide by minus 2. Well, this becomes cosine R1 cosine R2 minus sine R1 sine R2. All right. Take a deep breath of relief. That's what we were trying to show here. A little arcane, you know, kind of some heavy lifting here. As I said, you know, you won't have to reproduce this on the final. I guess maybe that could be an extra credit, right? All right. So out of all that, we just get this nice formula here. Any questions about that? Because we're going to move on from the proof. All right, it turns out, as I said, once we have this nice formula, that a lot will follow from it. Okay. First thing we want to do is we want to take this and we want to use it to develop our next formula. So we're going to start with one of the co-identities, cosine of 90 degrees minus, we'll just say A for now, equals the sine of A. So how am I going to apply this here? Well, I'm going to say that the sine of x plus y is equal to the cosine of 90 degrees minus x plus y. That's just a direct plug in here. And I want to rearrange this a little. I want to call this the cosine of 90 degrees minus x minus y. I jumped ahead a step. I have to back up a little. Before I do this, really what I want to know is, what is the cosine of x minus y? That's really easy. Cosine of x minus y is just the cosine of x plus minus y. I have a formula for x plus y, x plus something, so let's go ahead and plug this in. This has to be cosine of x, cosine of minus y, minus the sine of x, sine of minus y. That's what cosine of x minus y must be according to this formula. Well, I can simplify this using my odd-even identities. Cosine x, what's the cosine of minus y? Okay, we all know this, cosine of y. And sine of x, that's fine. Sine of minus y minus the sine of y, because it's an odd function. So sine of y, but there's a minus 1 here, so I get a plus. This cosine of x, cosine of y, plus the sine of x, sine of y. You'll notice these look very similar. You just have to remember that when you add cosine, when you add x plus y to the cosine, you get a minus here. And when you subtract, you get a plus. We sometimes write these both together this way. We say plus or minus here, we'll say minus plus here. It's just a shorthand. You get 2 for the price of 1. Okay. Back to my sine of x plus y. I needed cosine of something minus something. Okay. So cosine of 90 degrees minus x minus y, let's apply that second formula. That'll be cosine of 90 degrees minus x times the cosine of y minus, no, this is a minus, so it's a plus, sine of 90 degrees minus x, sine of y. Okay, but now I have to use my co-function identities. They're already becoming useful. The cosine of 90 minus x. What's the cosine of 90 minus x? I see they're already useful, but they haven't seeped in yet. And if I have a right triangle, and I have theta here, so which one am I going for? The cosine. So adjacent, the hypotenuse, so the cosine of theta is the adjacent over the hypotenuse. Now if I look at this angle here, it's the complement, so it's 90 minus theta. Right? What is A over H to this angle? What function goes here? This is now the opposite over the hypotenuse. What's the opposite over the hypotenuse?
Sine.
Sine. Yeah. So sine of 90 minus theta is the cosine of theta, and the cosine of 90 minus theta is the sine of theta. They're co-functions. So this becomes sine of x, cosine y. This becomes cosine x, sine of y. So that gives us our second formula. Sine of x plus y is sine x cosine y plus cosine x sine y. Okay, it's a different pattern, right? Here we have cosine, cosine, sine, sine. Here it's sine, cosine, cosine, sine. Oh. Yeah. Sine, cosine, cosine, sine. Okay, that's our third formula. And we didn't really have to do very much. We just had to plug in using our cosine and find cofunctions. There it is. Very important question in math education is, which is more important? I mean, certainly the end results are important, but the journey to get there is important too, right? I mean, I suppose if you're going to be a surveyor, maybe just the end results will do. If you're going to be a mathematician, obviously you really need to understand the journey, but as students, I don't know. It's controversial. Okay, we of course want to find the sine of x minus y. But again, sine of x minus y is just the sine of x plus minus y. We have a formula for this. It's sine x cosine minus y plus cosine x sine minus y. And here again, we're going to use the odd-even identities. Cosine of minus y is just cosine of y. Cosine of x, sine of minus y is minus sine of y, so I just need to make this a minus. So once again, you can see I can use a little shorthand here. I can just put a minus here and a minus here. And you just have to understand sine of x minus y is sine x cosine y minus cosine x sine y. There's a certain symmetry to these formulas that it's not really an accident. accident of fate. Right? Well, that's obviously the next thing I'm going to do. Got the sine, the cosine of x plus y, the sine of x plus y. What's missing? Tangent. That doesn't seem all that hard at first. The tangent of x plus y, of course, is sine of x plus y over the cosine of x plus y. We have formulas for these. Right? We have sine x cosine y plus cosine x sine of y over cosine x cosine y minus sine x sine y. That's kind of busy. It'd be nice if we, A, could simplify that, and B, put it in terms of the tangent. It'd be nice if the tangent of x plus y could be put in terms of the tangent of x, tangent of y. So, what we do is we multiply this by 1 over the cosine x cosine y over 1 over cosine x cosine y, and multiply it by 1. So what do we get? We get sine x cosine y over cosine x cosine y. More of this little green stuff here, aren't I, than I thought. Cosine x sine y over cosine x cosine y. And on the bottom, we have cosine x cosine y over cosine x cosine y minus sine x sine y over cosine x cosine y. All right, let's see, what can we do here? These cosines cancel. These cancel. These cancel. We just end up with 1. So what do we have? Sine x cosine x. That's the tangent of x. Plus sine y over cosine y. That's tangent of y. Over 1 minus, what's this? Sine x over cosine x times sine y over cosine y. Tangent x, tangent y. So all these just, it's just kind of magical. They all just kind of pop out of that original proof. All right, so what did I say? It was tangent x plus tangent y over 1 minus tangent x tangent y. Let's think for a minute. Sine was an odd function. Cosine was an even function. Sine over cosine is a tangent. What kind of function is the tangent function? Is that an odd or an even function? Anyone recall?
Odd.
It's an odd function. Yeah. If you think about it a little, if you multiply an odd by an even, it's got to become an odd function, or if you divide. So, x minus y, well, tangent of minus y here will become minus, right? Tangent of minus y is minus tangent of y. tangent of x is tangent of x. Tangent of y, again, minus tangent of y. So we get a minus, if you write that properly, minus plus. Okay, so here we have our three basic addition formulas. We could really grind you into the dirt here by trying to do the cotangent, the secant, and the cosecant. It's not necessary. We can always express the cotangent, the secant, and the cosecant in terms of sines and cosines, so it's not really necessary. If you really like math and you think you're going on, go for it. Figure out what those formulas are. But these you really will need. The first two, the most. All right, where we go from here, we're gonna come up with some more formulas, but they're gonna be easy formulas. Before we do that, I'd like to at least show you one example of why this might be useful. Let's say I wanted the cosine of 75 degrees exactly. I punched into my calculator with a decimal expansion that I don't understand. Well, if I notice that the cosine of 75 degrees is the cosine of 45 degrees plus 30 degrees, well, the sines and cosines of these I have exact values for, right? So we know this is the cosine of 45 degrees. Cosine of 30 degrees minus sine of 45 degrees, sine of 30 degrees. And then we just have to remember our special angles and their values. Well, cosine of 45 degrees is 1 over the square root of 2. Cosine of 30 degrees. Square root of 3 over 2 minus sine of 45 is again 1 over the square root of 2. Sine of 30 degrees is a half. So I get square root of 3 over square root of 2 over 2 times 2. Oh, minus 1. Square root of 3 minus 1 over 2 square root of 2. And if you don't like the radical in the denominator, we can get rid of that. That's square root of 6 minus square root of 2 over 4. Now, I just listed one combination, but there are a lot of combinations you could come up with, right? We could say, what's the cosine of 15 degrees? Well, that's the cosine of 45 minus 30 degrees. So there's a host of angles that we can now find exact values for. All right. The next formulas are kind of simplifications. I'd like to know what the cosine of 2x is, a so-called double angle formula. That's not too hard. That's like the cosine of x plus x. Well, that's cosine x minus sine x sine x. So that's cosine squared x minus sine squared x. Now, this particular formula is special. You're going to be able to use this in some substitutions, but not always in this form, right? You look at this and it makes you think of something, right? Think a little of the Pythagorean identity. Well, if I take cosine squared x minus sine squared x, that's my cosine of 2x. Well, I could add something to this. I could add sine squared x plus cosine squared x minus 1, right? I could add this. That wouldn't change it, right? Because sine squared plus cosine squared is 1. But if I do that, what happens? The sine squareds drop. I get 2 cosine squared x minus 1. So this is another way to express this. However, I could just as well have subtracted this. So let me distribute minus plus. Now when I add these, what happens? The cosines drop. I get a positive 1 and minus 2 sine squared x. So this is 1 minus 2 sine squared x. All of these are equivalent. All of these are the double angle formula. But there are times when one or another of these versions will come in more useful. Sine of 2x is not quite as flexible, but maybe easier to remember. Sine of x plus x is what? Sine x cosine x plus cosine x sine x. Well, that's just 2 sine x cosine x. Well, that leads us back once more to the question of what the tangent of 2x is. Well, we have some choice here. Tangent of 2x equals sine of x, that's fine, 2 sine x cosine of x. What could we use here? Well, it really matters, actually. Let's try cosine squared x minus sine squared x. What could we do to make that a little nicer? Well, why don't we try multiplying this by 1 over cosine squared x. So on top, I'm going to get 2 sine x cosine x over cosine squared x. On the bottom, I'm going to get cosine squared x over cosine squared x minus sine squared x over cosine squared x. One of these cosines is going to cancel. So I'm going to get 2 tangent of x over 1 minus tangent squared x. I guess I could have used this instead. That probably would have been smarter. 2 tangent x over 1 minus tangent squared x. Okay. We're almost out of rope here. Almost out of time, aren't we? Yeah, I think I'm going to stop here. We have a few more formulas to develop. You might want to check out the homework, the part where we do sums and double angles. You can see something that goes beyond that to half angles and so forth. Put it off for now. Any questions before we go? Okay. All right. Thank you.